All right, moving along to the next topic, we are making plans for Moon over Monona Terrace, which is coming up on Friday, October 15th. And we are going to be having that event online just like we did last fall due to health concerns with the pandemic. So it's looking like we're going to have a similar format as we did last year with a couple of live channels, hopefully with a couple of live telescope feeds, and also a channel with some pre-recorded material. So if anybody's got an idea that where they would like to do a presentation for an all ages audience that, you know, lasts 10 or 15 minutes long and record that, we would be able to put that up on the live channel. So if that's something that might interest you, contact me. And also, if you're interested in helping out with a live telescope feed, also let me know. So there's plenty of time to plan it out, but that's kind of what we got cooking. Does anybody have any questions?
Just a comment, Lawrence, for the membership that may not have been in the meeting or heard about it. When we talked to Mindy, she didn't really want to press us one way or the other, but when we made the decision that it should be virtual like last year, she was obviously relieved. And I think she shared our sentiment in terms of the concerns to working with kids and stuff like that in close proximity. And she supported that decision.
And Kevin's referring to Misty, who's the events coordinator at Monona Terrace.
Right.
We've been working ever since I've been a member of Madison Astronomical Society. She's been really great in helping us put on these events. Does anybody else have any questions? All righty. And just so you know, I think a friend of mine who isn't a member of the club already bought a ticket on Eventbrite. So I think if you go to the Monona Terrace website and you're interested in getting a ticket, of course, there's no limit to it, but it's a pre-registration so that you'll have access to all the live video streams.
I went online and ordered a ticket today.
Great, great. Yeah, so now's the time to get your registrations in and join us for Moon over Monona Terrace online. Another event that's coming up at UW Space Place, they are having a limited attendance at UW Space Place, a limited attendance in-person lecture that I'm trying to find in my email. And they're also going to simulcast it through the Space Place YouTube channel. But on September 14th, I believe September 14th is a Tuesday, right? Yes, I think that's right. I didn't write that down.
That is correct.
Yes, it is a Tuesday. On Tuesday, September 14th at 7 o'clock, they are going to present a tour of the universe. You Are Here with hosted by Dean Regas, astronomer of the Cincinnati Observatory. And here's a little description of the event. Rocket through space and sail among billions of stars and galaxies. Using some amazing simulation software, Dean Regas will guide you through a mind-boggling scale of the universe. Along the way, you'll stop at the moon and individual planets, and then you'll make a jump to light speed and head to interstellar space to see the galaxies in the universe. Don't worry, we'll have you back home in time for dessert. So that's going to be in person, but they're going to have limited attendance there, and masks will be required. And also, as I said earlier, they're going to have it broadcasted on their YouTube channel. All right, hopefully I'm not forgetting anything. Another important announcement, it's looking like we haven't finalized this at our upcoming board meeting yet, but it's looking like at the October meeting, we're going to want to achieve a quorum to have a brief formal meeting and discussion of the general membership of the Madison Astronomical Society. What's going on is we are planning to upgrade the AMP service at Yana Research Station, our dark sky observing site, which currently has electrical outlets for a few of the pads and some other electrical issues that cause certain circuits to trip out regularly. So what we're planning to do is upgrade from our 100 amp service that we currently have up to 200 amp service. And we've received a quote, an acceptable, what looks to be a good quote from Hill Electric to upgrade that amp, to upgrade our circuit breaker, and also add a couple of nice features to it. But the reason we're having the meeting is the cost of this project will exceed the $1,500 discretionary limit that the board is allowed in the bylaws of our organization. And then what we're going with this upgrade too is we want to increase the number of pads and the number of outlets for the higher number of pads out at Yana Research Station, so more people can use the site at the same time. And that this is going to be a project that's going to have another phase up and beyond upgrading our electrical service. Is anybody, yes, Jürgen?
I just wanted to add, you kind of said it at the end, but we're looking at doing this, having the pads installed. This is phase one. Phase two is pads and some other infrastructure. Probably will happen towards the end of 2022 if we're lucky. There's a lot of planning that has to go in, and we're looking at some general contractors who are already booked out into next summer. So the electrical part is the easy part, or this part of the electrical project is the easy part. The hard part will be coming, and the planning will involve everybody in the club at some point to comment on what we plan to do. But there will be a comprehensive plan coming along, hopefully before Christmas if we play our cards right.
Yeah, the only thing we're trying to do right now is to upgrade the electric to 200 amp, and that's kind of a predecessor task for anything else we might want to do in the future.
And the one thing Lawrence mentioned, there are two little things that go with it. One of them actually is surge protection for the entire site.
Yeah, and that'll be really great to have. And I think when I first joined the club around 2012, I think we had roughly 60 or 70 memberships at the time. And we've essentially almost doubled the number of memberships. So looking, once the pandemic settles down, there could be a lot of high demand usage for Yana Research Station. So we want to make sure that everybody has an opportunity to use the site and use it comfortably.
For people who like numbers, we hit 136 members today, and slightly more than half of them are observing members. So we are talking about 60 odd observing members, and with 6 pads out there, that's obviously not enough. And I'm not sure, we're not going to get 66 pads out of YRS, I can tell you that.
We are working on getting more. Does anybody have any questions or concerns?
Lawrence, I just have a quick question. I assume Wi-Fi will be part of this. Is that right?
No,
That is something I would really like, and I think it's getting cheaper and cheaper to do that, but we haven't quite dipped our toe into the details on that yet. Does anybody want to add anything?
Yeah, I was just going to say that we've discussed at some point in the future, maybe doing some Wi-Fi, but again, we want to update the electrical first only. That's all we're trying to do at this point.
there are actually 2 elements to Wi-Fi. One is controlling your mount from the clubhouse, and the other one is controlling it from home. Controlling it from home, which really applies to the DGRO, that becomes a real mess because you have to worry about weather, about closing down the mount properly, closing things. There's a lot of work that would have to get into doing that. If you want to do Wi-Fi from the clubhouse, you can actually do it yourself because you can supply the router yourself, and then you can sit in the clubhouse and do everything you want.
Yeah,
It might be interesting too if we could put like an all sky camera there so people could check what the weather looks like down at the YRS.
If we're going to have Wi-Fi from off-site, that is mandatory,
Yeah.
and that would be, those cameras really are not that expensive.
No,
no, not
they're
at all.
pretty cheap.
And just to wrap up the discussion, because we are past the 7:30 start time for the presentation, but we also want to have, because reception is spotty out there for cell phones, and it would also be a nice way to have, if people have an emergency out there, to be able to contact people without having to rely on cell coverage. So
What I was going to say is that we have a committee within the town of Brooklyn that has been looking at expanding the service in the area for both cell and for digital. There's a number of different options right now, and we're kind of in a race of which one is going to prevail, if it's going to be Frontier Telephone, or if it's going to be
Frontier fiber optic.
the fiber optic, or if it's going to be one of the towers that are around here that they're expanding.
Wireless DSL.
And we have wireless DSL, if you can get it close enough to some of the Frontier lines. Right now, it's too far away, but they're talking about expanding in the near future.
Thanks, Kevin. All right, and we are out of time. John, would you like to introduce tonight's speaker?
With pleasure. Bob Hamers, why don't you go ahead and turn on your screen sharing while I'm introducing you. As I mentioned last month, tonight is the third consecutive meeting where we've had one of our own speaking as the guest speaker tonight. So I'm delighted to introduce Bob Hamers. Many of you know Bob. He's been a club member for relatively short time, Bob, maybe 4 or 5 years, maybe a little longer than that, I think.
Yep.
But in that time, Bob has quickly established himself as a maestro of astrophotography and helped us out with a number of public events as well. So Bob is going to address his astrophotography tonight. Specifically, he's going to talk about solar imaging. Bob, how's it going there? Are you sharing yet? I can't see.
Yep, you should be able to see it.
Are people seeing Bob's screen?
Yes, I see it.
Okay.
Yeah,
Bob,
I've got it.
You are good to go, Bob. Take it away, everybody.
Okay.
Welcome, Bob Hamers.
All right, thanks, John. It's really fun to come and tell you a little bit about what I've been doing recently. So John said I'm going to talk today about some of the work in solar imaging. Let me emphasize at the beginning, I'm not a solar physicist. I'm not an astrophysicist. You know, I'm an amateur guy who likes to image the sun. And so I've been learning a lot, and both about how to do it and also what am I actually looking at. So I'm going to focus this along the lines of kind of what can you do with an amateur level telescope rather than what can you do, say, with the Hubble Space Telescope, and what is some of the things that kind of control what you can do. Just to start off with, I know John asked me to talk about like how I got into astrophotography, and this is my grandfather. Back in 1960, he was a machinist. He made this very large Newtonian telescope, so a 12.5 inch. He made everything in his basement, and I remember as a kid standing up on this really tall ladder to look at the moon through the eyepiece, which must have been like 10 feet off the ground on this thing. So I've been interested in astronomy for a really long time. What really got me interested in more the solar aspect of it, like many people in 2019, I went down with Jean, my wife, down to Missouri to look at the solar eclipse, and the weather wasn't so good that day, but it pretty much cleared up during the time of totality. And I got my wonderful images of the corona. And then afterwards, I came back and I was like looking at these images that I got, and I noticed this funny little thing over here, which is this little thing of red. And I thought, well, what the heck is that? You know, I thought this was like a lens flare or a problem with my camera or something. And then I messed around with contrast more, and I got it to be more pronounced. And then I went and looked at some of the images that were on the internet. I realized, my gosh, I could actually see solar prominences with just a plain old everyday camera. And all these red things were like the hydrogen alpha emission from these solar prominences. So I thought that was really cool. And that really got me interested. And then more recently, I've just been interested in it because it's kind of a daytime activity. So, you know, why would people be interested in solar imaging? Well, it is our closest star, so you can see lots of things that you can't see in any other star. Living in a city, we hear a lot about light pollution, but there's almost no such thing as dark pollution. There is smoke. We do have to worry about that. But you don't have to worry about dark pollution. Works from your backyard. You don't have to travel. Images come really fast, a millisecond. I'm going to show you that the sun is new every day. So even if you're imaging the same object, there's always something new to look at. But what's surprising, actually surprised me, is that you can really see changes over a time span of several minutes or less. And we often think of astronomical objects as being static, but I'll show you that in fact, there's many things that are happening in a time scale of minutes to seconds that you can actually observe. Daytime astronomy avoids sleep disruption, and that is also more consistent with still working a full-time job and not having to go to work sleepy, because I can do this on the weekend and not mess up my sleep schedule. Okay, so I'm going to talk a lot about the sun, and I'm going to kind of divide the talk into two parts. And they really correspond to what it is that we're trying to look at. So the important thing is the sun is kind of like a big onion. It's got different layers. And we're going to talk mostly about two different layers. We're going to talk about the photosphere. And the photosphere is where sunspots are. It's the really bright part of the sun. It's what you actually see when you're looking at the sun under ordinary conditions, okay? But then on top of the photosphere is another layer called the chromosphere. And the chromosphere is it's a less dense layer, but it is really where all the action happens. And what we'll see is that the photosphere, for example, emits light at all wavelengths, and there are features you can see on it, but not nearly the level of detail and really fine detail that you can see in the chromosphere. And it basically is revealing a lot about what the magnetic field of the sun is doing. So I'm going to talk a little bit about both of these. I actually like the chromosphere much more. I find it more interesting, but we have to talk about the photosphere first. So because of these differences between the photosphere and the chromosphere, there are basically two ways you can think about imaging the sun. One is to essentially image what I'll simply call continuum or white light imaging. If we look at the emission from the sun and how it varies as a function of wavelength, going from the ultraviolet all the way out to the infrared, the visible being this range between about 400 and 700 nanometers, this little range in here. When we look at the sun in all wavelengths, we tend to see something that is relatively featureless. We can see sunspots, we can see the umbra and the penumbra. There's some other details that we'll talk about in a little bit. But if we look at that spectrum, on top of the broad feature that we would see with white light, there are some extremely narrow absorption lines, these little dips that are going down. And these correspond to absorption. They correspond to things that are in the chromosphere that are absorbing the light that's being given off by the photosphere, right? So we've got this very bright photosphere. It's giving off light at all wavelengths. And then we cap that off with this chromosphere, which is what we actually want to look at. So the chromosphere absorbs these very, very narrow wavelength regions. And so we can look at the photosphere, looking at all wavelengths, and we can look at the chromosphere if we can select so that we are only looking at these extremely narrow wavelength regions where the chromosphere is absorbing that light from the photosphere. And one of the common lines that we often use for doing that is called the hydrogen alpha line. Okay, so we'll talk about hydrogen alpha imaging and continuum imaging. These are actually two images of exactly the same region of the sun taken on exactly the same day, simply looking at white light and looking at hydrogen alpha. This sunspot right here is this sunspot right here. These two features here are sort of difficult to make out here, but they're roughly here and here. And I hope you'll see that there's a lot of detail in this H alpha image that is not at all reflected in the continuum image, right? So a real driving force for going down to the chromosphere level of imaging. Unfortunately, chromosphere imaging is also fairly expensive. And so a very common way to begin in solar imaging is just by imaging in white light. You can do it with a standard telescope with relatively small investment. The most common way of doing that is to simply take a regular telescope and then to put over that a very thin film, usually metallized mylar, that just blocks almost all the light. right? You don't want to have sunlight going into a 9-inch telescope and frying everything or setting things on fire. So basically, you just want to knock down the intensity of light to a low enough level that it doesn't hurt anything behind it. So I'll show you a few images I took with this telescope. This is my Celestron 9¼ inch Schmidt-Cassegrain telescope, and then just a video camera in back. One of the differences between solar imaging and deep sky imaging is that with solar imaging, there's a lot of atmospheric turbulence. And so the usual way that you do imaging is to do what's called lucky imaging, where essentially what you do is you image very quickly, like millisecond exposure times, and you take thousands of frames. 1,000 or 2,000 frames is not at all unusual. And after you take all this data, then you sift through it and have an automated program identify what are the really sharp frames in that image, and then merge those into one final image. There's another way you can do it using a Herschel wedge that I just really won't talk about, but if anybody has any questions about that, that's fine. Okay, so this is the telescope we're going to start off with to do continuum imaging. And again, here's some examples of what you can see. So again, you can see sunspots. Oftentimes around the sunspots, you can see these whitish regions. They're a little hard to see in this particular image. These are regions called Faculae that I'll talk about in a little while later. On a good day, you can see some fairly detailed images of sunspots. So these are images that I took about 3 weeks ago. I should say all the images in this presentation that are in black and white are mine, taken within the last year. I'll have a few that I've taken from other places and usually identify them. But again, these are things that I took in my backyard using telescopes that are, again, amateur level telescopes. So here's a fairly complicated sunspot complex where, again, you can see the dark region that is the penumbra. You can see the lighter region around it, the umbra. The umbra often has these kind of finger-like structures going out from it. You can see pores. So pores are small regions. Like sunspots, they're cooler than the rest of the region around it, which is why they're darker. But these are small enough that they don't have a kind of a umbra and a penumbra. They just have a little dark spot. And then on a really good day, you can also see what's called granulation. So the sun is very turbulent. And within this photosphere, there's lots of ionized gases that are bubbling up to the top, and they form these convective layers. That's called granulation. And so on a good day, you can see the fine details of this granulation over here. I'll show you a blow up of that in a minute. So this is done just with a $100 simple white light filter over the front of the camera. Now you can compare that with like a Hubble Space Telescope image, all right? And okay, they show better detail and everything, but you know what's really amazing, I think, is essentially you can see all the features that the Hubble Space Telescope sees, maybe not quite as well, but you can see these things with amateur level equipment. So here again is the fine detail of the sunspot. Here's the granulation around a pore, right? Clearly better, but you can basically see these things in a standard amateur level telescope. Here's a really good version of that. Again, just lots of fine detail. These granules are pretty small on the scale of solar phenomena. One rule of thumb I always use is that the sun is 100 times as big as the Earth, okay? So when you see like the limb of the sun or a section of the sun, you can kind of eyeball roughly how big are things compared with the Earth with that little rule. These granules are about twice the size of Wisconsin. Okay, so they're big, but not as big, say, as a sunspot, which can easily be like the size of the Earth almost. Now, what I find really interesting about the sun is it has weather. And whereas weather on Earth is created by temperature differences, weather on the sun is mostly created by magnetic fields. So the sun has lots of ionized gases on it. So it is gases that are atoms that have lost an electron or gained an electron and therefore are charged. So that turns out to be very important because the sun, like the Earth, has a magnetic field, right? So north and south. The sun's magnetic field is only about twice as big as that of the Earth, all right? But because of the fact that the sun has all these ionized gases, and you might remember from high school physics that a charged particle moving in a magnetic field feels a force on it. So as the sun rotates and moves these ions with its magnetic field, it distorts the magnetic field of the sun. And that distortion of the magnetic field is essentially what gives rise to many of the interesting features that we'll look at. It gives rise to sunspots, so regions where there's like turbulence or kinks in the sun's magnetic field. It gives rise to certain kinds of prominences where that magnetic field leaps out of the sun and then kind of comes back on itself. So pretty much everything we see, especially when looking at the chromosphere, is tied in with the magnetic field of the sun interacting with all these ionized gases. But it's weather, and like weather on the Earth, the weather on the sun changes every day, and you can see it, and you can infer what's happening at a very detailed level by looking at sunspot images and other things, much like you can infer the weather on the Earth by looking at the top and looking at the clouds. You can infer what's going on underneath. In the same way, when we look at the sun and we look at the chromosphere and the photosphere, we can get a lot of insight into what's going on underneath in the regions that maybe we can't directly see. And hopefully, okay. So I mentioned that one of the things that creates much of the structure that we see on the sun is magnetic fields, and this idea that the magnetic field of the sun, coupled with its rotation, pushes these magnetic fields out and they come back. And so this is how sunspots are created. They're like kinks in the local magnetic field, and they often appear in pairs. And you'll see this in the images that I show, that you very rarely will see one sunspot all by itself. It's usually paired with other sunspots or sometimes other structures that may not look like sunspots, but have many of the same physical phenomena. You'll also see that this gives rise to an interesting phenomena when we look at the chromosphere. You're going to see a lot of detail that's associated with what I'll simply call flux tubes. Ions in this magnetic field circle around in little spirals, and these spirals make tubular shaped structures like these fibrils at the edge of the sunspot, and things that give rise to a lot of very fine detail having to do again with what is the magnetic field of the sun doing as a function of position. Here again is this granulation, just in higher resolution. But again, the photosphere, we're kind of dominated by these granulation cells where we have these hot gases coming up, moving off to the side, and we form these structures like the one that I've shown here. There are other things you can see. So although I emphasize that with white light, mostly what you see are sunspots, the dark umbra and the lighter penumbra, you can begin to see other things, especially when a sunspot is near the edge of the sun, what's called the limb of the sun. You can see other whitish regions called faculae. This is what they look like in white light. This is a narrow band imaging, meaning a selective wavelength looking at calcium, where you can see many of these same kinds of structures. So these are actually now revealing more information about what's going on with this granulation. So what ends up happening is these granules. I should point out, I mentioned earlier that there's a lot happening in the sun and it's dynamic. So this is like a Hubble Space Telescope image. Obviously, this is not a backyard image, but this is looking at how this granulation changes over a time period of about an hour. Okay, so the important thing that I want to get across here is that the sun changes, and it changes on a time scale of 10 minutes, easily visible in what's happening with this granulation structure. So these facula are kind of interesting because they tell us a little bit about the disruption of that sun's magnetic field. So when we have these little convection cells, these little blue boxes kind of represent what we're looking at from the top here. Right now, we're looking at the top of these things. When we're looking at the edge of the sun, we can begin to see the sides of these little boxes. So these little granulation cells where we have stuff moving up and then moving down. If we're looking at it from the top, we tend to see one thing. If we look at it really steeply, we see it from the side if these granulation cells are kind of bobbing up and down. Okay, so that's basically a sign of like magnetic turbulence. It means that these granulation cells are not nice and uniform and smooth, but in fact, they're kind of moving up and down, which gives us a chance to see what's happening along the sides, and the sides are very bright. I didn't point out earlier, you can see that the region between these is often very bright as well. All right, so the important thing is the sun is dynamic, and you can see these changes. Now, what I want to move on to and talk about for most of the time is hydrogen alpha imaging. And this is really focused on imaging the chromosphere, that outer region of the sun, where we're looking at absorption of the photosphere by this outer region. And the important thing from a practical standpoint is that this layer is very thin. I'll show you later, you can see directly how thin it is, but it's cooler, or actually, I'm sorry, it's a little bit hotter, but it's less dense than everything. But this chromosphere absorbs light, which means sometimes you'll be looking for things that are dark locally. And then there are certain features on the chromosphere that are bright. So interpreting what's happening on the chromosphere is a little bit tricky, right? Sometimes you see that a structure will absorb the light from the photosphere and it will appear dark. Sometimes it will actually be emitting even brighter than the underlying photosphere, and it will be bright. So interpreting it is a little bit tricky sometimes. Now, what's difficult about hydrogen alpha imaging is that this absorption line here is very, very narrow. And so if we want to see what's happening at this very specific wavelength and not what's happening all the wavelengths around it, we need to design a filter that can selectively image at this one very narrow wavelength. And the important point is that this absorption feature is very narrow. This goes from 656.2 to 656.4 nanometers. So 0.2 nanometers, or only 2 angstroms. I'll just point out that for many people who are used to doing like deep sky imaging, where you're looking at galaxies or more typically nebula with a deep sky hydrogen alpha filter, those filters are typically have a width of anywhere from maybe 5 to 7 nanometers. What we need in order to do this hydrogen alpha imaging is a filter that is about 100 times narrower than a standard H alpha nebula filter. Okay, so that's the trick of doing hydrogen alpha imaging. And the way to do that is to use this device called an etalon. I'm not going to go into detail on an etalon, but understanding a little bit, it is important understanding how a solar telescope works and why it's able to image with such good resolution. So an etalon is a kind of interference filter. It's simple in principle. It's 2 pieces of glass that are metallized to about 90 to 95% reflectivity on both sides. So light coming in partially gets reflected and caught in this little region of air, about 1/10 of a millimeter thick, between these 2 glass plates. And it happens that if the distance between these plates is exactly an integral multiple of the wavelength of light, the light will be transmitted, and otherwise it will be reflected. So if you look at like a transmission spectrum going through this filter, what you see is a comb-like structure, very narrow peaks where the light gets transmitted, really sharp, 7/10 of an angstrom is not unusual, but there's a lot of them, right? Many, many, many different wavelengths of light can come through at the same time, and these are separated by only about 10 angstroms or 1 nanometer. This can be tuned in a couple different ways, but one way of tuning it is to tilt the glass a little bit. That changes the effective distance that the light goes. And so this etalon, which is the one that I actually have on my scope, is a tilt-tuned etalon. It's got a little wheel here, and I can tune the wavelength. I can move this whole comb structure back and forth a little bit by turning that little wheel. So to make a solar telescope, this is basically the outline of everything we do. We start with the sun spectrum, the visible region going from like 400 to 700. We slice out a region of that, so we only pass, say, between 600 and 700 using something called an energy reducing filter. That's the purple on the top of this, right? So that wavelength distribution would look something like this. Now we pass that light through our etalon. So here's our etalon into our ordinary refractor telescope. And then at the bottom, we've got to have a really narrow filter again, right? So all these different comb-like structures will transmit. So what we need is a very narrow filter that will transmit exactly one of these. So this filter needs to be about 1 nanometer in bandwidth, needs to be narrower than the distance between these peaks. But if we have this selected right and it's lined up with one of these little very narrow features, then we get the width of this feature passing through. Okay, I know it's a little bit complicated, but kind of this is the way the etalon works. And so then by tilting this etalon a little bit, we can change the wavelength it's getting through and record it on our eyepiece and camera. For anybody who's interested in like buying a solar scope, there's a couple different ways you can do this. I'm using what's called a front-mounted etalon that fits right on the front of my scope. In a lot of ways, that's the best kind of etalon, but it's also the most expensive because it needs to be big. It needs to be pretty much almost as large as the objective of the telescope, which means it's also very expensive. Most of the solar scopes, instead of putting it on the front, they wait till the light gets narrowed down to some smaller diameter within the scope, and then they put the etalon and the other filters. There's some details here that I won't go into that make it not quite as simple as it might be. But anyway, this is what a typical solar scope that you might purchase would look like. And these etalons are sometimes controlled by changing the air pressure. If you change the pressure of the air in that etalon, you change the index of refraction of air, and that also will change the wavelength rather than tilting it. Okay, so I'm gonna do everything with this kind of front-mounted scope. Here's what my scope actually looks like. So it's a Takahashi 900 millimeter refractor. I then have these 2 etalons. They're pretty big. They weigh 5 pounds each. I have 2 of them so that I can get down to the narrowest possible wavelength. And then I go through a long chain, an extender, and then down to a video rate camera. One of the difficulties of working in sunlight is it's really hard to see your laptop if you're trying to do recording. So I also have this ultra bright display that's about 10 times as bright as a normal laptop computer display. And that allows me to actually like sit here and tune the wavelength of this filter and directly watch what's happening right here. And then it's on wheelie bars so I can wheel it around the backyard. So this is what a typical full disk image of the sun would look like in H alpha. And immediately, hopefully you're struck by the level of detail that you can see. The whole surface is covered with something that we often describe as an orange peel effect or dark mottles that I'll talk about later. You see some locally dark regions. So this one right here, that's called the filament. There's another small one over here. You can see sunspots. So there's little sunspots over here. You can see what's called plage. These are very bright white regions that occur on the center of the disk that I'll talk a little bit about later. You can already begin to see like these lines forming here. I mentioned and emphasized how we trace out the magnetic field of the sun. And you'll see that beginning to form here, where instead of having these dark models, we've transitioned over to new structures that occupy actually quite a bit of real estate, much larger than the size of the sunspot itself. And then sometimes we can see a solar flare. This bright spot right here, this arrow unfortunately is pointing in the wrong place, but this really bright spot here, this is brighter than the photosphere itself. And it's solar flares are what basically give rise to these cascade of ions that ultimately cause the aurora borealis and other effects on Earth. This is a small one, not a big one, but These are things that are actually like really active on the surface of the sun. Now, I really like high resolution images. I am just enthralled by understanding and looking at all the fine detail that occurs when you look at hydrogen alpha. So here's an example where we're looking at a couple different sunspots. I mentioned again that sunspots almost never occur alone. They usually occur in pairs or groups of 3. Here's one sunspot, a couple of little pores or burgeoning sunspots here, another one here, and an interesting structure here. This is what's, again, this stuff called plage, which is a very active region for bright emission by the sun. You'll see dark regions. And again, when you think of this, you have to think about when you see something that's dark, really what it means is it's absorbing the light from the underlying photosphere. And when you see something bright, it could either be letting the photosphere out, or it could be actually emitting itself. And that's part of the difficulty of interpretation. Then you can see, again, filaments like this one and this one here, these dark regions. And I mentioned how you can see granulation. So granulation is this turbulent structure that occurs on a pretty small length scale. There's another length scale of what's called supergranulation. And these are bundles of what are called spicules. If you look at higher resolution, you see there's little spike-like structures that occur in these regions, and they're dark. And in the regions in between, it's light, and then a region almost of clustered little spikes, all right? So these are what give rise to that orange peel appearance, but it's a very characteristic length scale that's longer than granulation, but the entire surface is covered with these. So I'm always just fascinated by understanding like what gives rise to these very detailed swooping curves and what's going on. I also like to think of these as sunflowers. One of the first things that really struck me when I started doing solar imaging is oftentimes we see these regions like the one down here, where you see these lots of mottled little white structures, and you can see some of it here and around the penumbra. And it just reminded me of the little mottled structure on the inside of a sunflower. And then you have all these like striations going away, which are these fibrils. These are dark, thin filamentary structures that again are tracing out what is that magnetic field doing as it's moving away from that sunspot. Here's that. This is just another one. Hopefully it will, okay, there. Here's another image, again, the solar limb over here, the edge of the sun, sunspots viewed from an oblique angle. There are some interesting effects related to how a sunspot appears that I don't have time to go into, but you can learn a little bit about the internal structure of a sunspot by looking how its appearance changes as it goes toward the limb. And here you begin to see two sunspots that are just beginning to form. They haven't formed that dark umbra penumbra, but in H alpha, you begin to see this kind of mottled structure, which is the predecessor of actually forming a full-blown sunspot. In this region over here also, very bright regions of high intensity emission. This is kind of a pre-sunspot that's just beginning to form. So, what are we looking at? Well, I kind of emphasize that sunspots appear in pairs, and actually sunspots almost have a polarity. So you can actually measure what is the magnetic field doing around a sunspot using something called a magnetogram. And this is based on the fact that if we were to look at even more detail at the light absorbed and emitted by the H alpha region, the magnetic field actually influences that in a very tiny amount, something called the Zeeman effect, that allows you to see what is the magnetic field doing in a region spectroscopically by measuring the exact wavelength of that H alpha line. And so these magnetograms show what is essentially the North Pole and the South Pole of a pair of interacting sunspots. And you'll notice that the North Pole and the South Pole in the Northern Hemisphere are flipped from the North Pole and the South Pole in the Southern Hemisphere. Okay, so again, the magnetic field kind of flips. And again, these sunspots are where the magnetic field loops out of the sun and then loops back in, as shown here. And in the regions in between, it's very much like a bar magnet. You all remember your high school physics experiment where you take a bar magnet with a north pole and a south pole, and you put a piece of paper over it and you shake on some iron filings. And what you see is the iron filings following the curves of the magnetic field, right? This is essentially what we're looking at when we're looking at those detailed fibrils and all those swooping, very fine structures in the vicinity of the sunspots. We're really looking at what is the magnetic field doing, just like the magnetic field around a bar magnet that you all did in high school physics. Here's another example. Here's a fibril, or I'm sorry, a filament. Again, this kind of dark structure against the underlying background, and two of these regions where we have just lots of activity with these tiny little fibrils moving away from this active region. And then as we move away, we get back to the dark models. But you can see that the weather on the sun is affected over a region much larger than you would think if you were just looking, say, in white light, right? You'd think only the sunspot and nothing else around it. And here we see that it's affected over much larger regions than that. Here's another example. This is just actually just a altered version of the previous one. Okay, so anyway, this is kind of, you know, some of the things that you can really begin to see by looking at the solar images. Here's another example of looking at a double filament. So this is again a dark region in front of the sun. It's absorbing the light from the photosphere below, and we again see these dark, or I'm sorry, these emissive regions around here, and just lots of transitions between them. Okay, so I mentioned that you see these dark things that are called filaments, and that these are absorbing light. What I didn't emphasize is what is a filament, and it turns out that a filament and a prominence, here's an image where you can now see the edge of the disk, and you can see some prominences off to the edge. We'll look at more of these in just a few minutes. But these dark regions that you see on the face of the sun that we call filaments are exactly the same thing as prominences. So every once in a while, you can see something that we call a filaprom. So this is a filament where it's dark when viewed against the face of the sun. But if you follow that across the edge of the sun, now you see that it's bright, right? So you can really see the correspondence. So you can watch as a sunspot moves. So the sun, of course, rotates with a time of about 11 days. And so you can see that a filament on the face of the sun and a solar prominence are actually exactly the same thing, just viewed in different ways. This image I actually wish I had in brighter contrast, but this is a wonderful image where you can again kind of see that magnetic dipole pattern where these two sunspots are interacting, and you can begin to see the swooping curves in the regions in between, just like the iron filings on the bar magnet once again. But what I wanted to show you here is something different, which is that I've talked a lot about the difference between the photosphere and the chromosphere. And I said that the chromosphere is, well, I didn't say this, but I should have said it, is the chromosphere is very thin. Okay, it's not very dense, and it's also pretty thin. So it doesn't actually absorb all that much light. You can actually see the chromosphere directly if you image right at the edge of the sun. So if we take this little region and simply blow it up, you now begin to see this fur along the edge of the sun, right? And this fur has little spikes on top of it. This again is exactly the same thing as that granulation of those so-called spicules that we saw on the surface of the sun, right? We saw those dark regions where we saw these sharp little spike-like structures coming up and forming the supergranulation structure. If we look instead from the side, now we don't have, over here, we have to look at the photosphere and how it's modified by the chromosphere. But if we look right at the very edge, we can see just the chromosphere all by itself. And if we again blow this up even more, now you can begin to see these spike-like structures, these things called spicules that form. And again, lots of detail beyond just the prominences that everybody knows about, hurling large amounts of ions out across the edge of the limb. But you can begin to, now you can imagine that this is the layer that's doing all that absorption, right? When we're looking at the face of the sun in hydrogen alpha, it's only this very thin chromosphere that we're actually looking at and how it's absorbing all the light from the, a significant fraction of the light from the regions underneath. I haven't talked much about prominences. Prominences, you can see, again, I showed you a couple on the previous one. Here's a not very visible prominence. As it turns out, they're trying to see what's happening on the face of the sun and what's happening on the edge of the sun at the same time is very difficult. And so I just want to walk through how do you do that? Because oftentimes people get very confused by these solar images. One of the tricks people play is to mess around with the histogram. Those of you who are familiar with deep sky imaging know about stretching the histogram and how you try to enhance contrast in certain regions by altering the distribution of the histogram. When people want to look at sunspots or other structures on the face of the sun and on the limb at the same time, they play tricks with the histogram. You can do things like have the face of the sun appear more or less normal, but have the edge of the sun be inverted, because the brightness of the face of the sun is so much different from the brightness of the stuff at the edge of the sun that if you look at a histogram of those two, you've got a very clean separation. So by flipping the histogram over, you can make one of them a positive image and one of them look like a negative image, but you can see far more detail in this image than you could in this one. You can invert this and make the disk inverted and make the prominence a positive image, meaning bright. And then of course, you can apply color if you want. And just a reminder, essentially every really nice looking image of the sun that you've looked at has probably been colorized artificially, right? Almost all solar imaging is done either at one wavelength or white light, and then usually the coloration applied after the fact. Playing that trick, you can really begin to see now what's happening at the edge of the sun. So here's another example where I've inverted the disk. So again, instead of seeing those dark models, we now see light models. I point this out because this confused me so much when I first began solar imaging as to why my images looked so different than some of those published in other sites, right? And it turns out nobody ever said that they inverted the color scheme or the gray scheme from what you would normally expect. So here it's inverted on the disk of the sun in order to be able to see what's happening here and what's happening out here in the prominences and all these little structures out on the edge. Here's another prominence. These different kinds of prominences have names. This is called a hedgerow. Many of these are very stable and do very much. Some of them are active and actually change over periods of 5 or 10 minutes. It all depends on kind of the nature of that solar prominence. The image that I used for today's advertisement is again an example of one of these where I've inverted the disk. So you see the bright models instead of dark models. And that really allows you to be able to bring out the detail in the prominences along the edge and to be able to begin to see some of the spicules at the very edge, like the finest detail that you can see in the chromosphere, and just get a very beautiful image of what the sun actually looks like. Now I've emphasized that the sun is dynamic. And so I showed you an example of the photosphere and how looking in the Hubble Space Telescope or equivalent telescope, you can actually watch the sun change. I want to show you how an amateur astronomer can actually do this. So let me remind you that the way you typically image in solar is like planetary imaging, lucky imaging. You take about 2,000 frames at a rate of about 100 frames per second, very fast. And again, you want very fast very short exposure times. So you freeze in the turbulence of the air and you get one sharp image instead of a blurred image. And then you want to take a lot of those, because if the air is turbulent, you're looking for those very small number of times when the air is quiet and you've got the sharpest image, and you pull out those frames at the end. So to make a video, what you do is you record a bunch of time-lapse images, maybe 1,000 frames in one batch, and then you do that maybe once a minute or once every 15 seconds. And each one of those 1,000 frames becomes one, or each of those batch of 1,000 individual images, after you sort through them and you make them into one frame of a video. So a typical video has anywhere from 15 to 50,000 frames, and that is typically maybe 15,000 to 50,000, I'm sorry, typical video would have maybe from 15 to 50 actual frames in the video, which means you've taken 15,000 to 50,000 images in order to make that. That's actually more than a full-length feature movie, okay? So data handling is a little bit tricky, but there are some nice programs that are freeware that you can use to do this, so you can just start it and go away for a few hours and come back and it's all done. You don't have to sit there. But then you can make this into an animated GIF. So here's an example of 1 hour looking at a sunspot that I took last Saturday. So again, there's lots of very fine detail changes. Some of these may not be real, but you can see, for example, these regions, right? These dark absorbing regions, you can watch directly how they change over a period of an hour. You can see this region down here changing. If you look over here to the middle, you'll see this white region is a little solar flare, and you'll see it kind of changing pretty dramatically in brightness, right? Solar flares are known to flash on and off on a very short time scale. So you can see the solar flare. And then you can just watch the slower motion of these dark regions, like along here, where you can just kind of watch things moving. And this is where it really becomes clear that when you think about what are you looking at, are you looking at white on dark, or are you looking at dark on white? Kind of becomes important, right? Are you looking at the dark region moving, or are you actually looking at the white region moving? And this also confused me for a long time to really think about it the right way, and realizing that everything we're seeing in the chromosphere is almost always absorption of light coming from behind. And so what we're really looking at is dynamics of the dark regions, except for things like this little solar flare, where this is brighter than the photosphere behind it. And so it actually really does flash. Here's another image. This is about a 45-minute video. This one is not as good quality. The seeing was not quite as good. But again, you can get an idea of like what kinds of changes can you see on a time scale that, you know, of one imaging session, for example, you can see changes in the structure of these. This is also why it's important to image fast, because if you took one frame every second or frame every few minutes, like you might do in traditional deep sky photography, you'd be washing out a lot of these fine motions, and you'd end up with kind of a blurry image rather than something that reflects the real short time scale and the true dynamics of what's going on the sun. This is one of the, to me, it's one of the coolest images that I've gotten, partially because I didn't know it was going to happen. I was just imaging the edge of the sun, and this is a loop prominence. So again, I emphasize that oftentimes, like you have the magnetic field of the sun kind of spurts out from the surface and then comes back, right? Magnetic fields always form in loops. And these hot ionized gases, which is what we're looking at in these prominences, they want to follow that magnetic field. And so here you can see this loop kind of leaping out and then kind of collapsing, whether it's under the gravitational field of the sun or exactly what made it collapse. But this is about the size of the Earth, okay? The diameter of this loop is about the size of the Earth. And this happened in a total of 5 minutes, right? So I actually calculate like how fast are these gases moving? And it's like 50,000 miles an hour. It is just screaming, right? So how fast these things are moving. Here again, this is one of these filaments, which I emphasized before were dark, but this is an inverted image looking at this part of the sun. So this kind of amoeba or thing that looks like a slug sitting on the surface of the sun is actually a prominence that we're looking at on the surface rather than along the edge. Now let's see if I can. Okay, well, that's it. You know, my goal here was to kind of convince you that with kind of amateur level equipment, there's a ton of interesting stuff that you can look at in the sun. I don't profess to be an expert in all the details of what we're looking at, but there's just a fascinating richness of detail at multiple length scales and things you can see using scopes all the way from entry level up to very expensive. And I hope that there will be other people in the society. You know, Sunspot's going an 11-year cycle. We are moving toward the solar maximum. So the next few years will be really good for solar imaging. And so I hope that at least a few other people will join me in this aspect of amateur astronomy. So with that, I just want to thank a few people. Most of all, I want to thank my wife, Jean Hamers, for tolerating me being in the backyard and wondering what am I doing out there all the time. And today is also her birthday, so happy birthday to her. And then just a shout out to the Astronomical Society as a whole. I found it to be a fantastic organization in terms of building camaraderie and teaching people. Like I was really a newbie when I moved into this 5 years ago, and people in the society, especially Jeff Schockler, I'm going to give him a special shout out, to really gave me a big help when I was just getting started in the field. And with that, I'll just end. And if anybody has any questions or comments or whatever, I'm happy to try to answer them.
I got a question for you, Bob.
Yep.
Two-part question. First is about equipment, and the second part is about the sun. I don't want to be crass and ask you how much you've invested in equipment, because I'm sure you don't want to talk about those kinds of actual numbers. But let's just take a theoretical person who has a decent refractor, who has a pretty good video camera, and they probably bought a white light filter, so they've done some solar imaging, but they want to move into the realm that you're talking about here. What, approximate cost for the that double stack filter, the Etalon, I think it was called, and some of those other accessories, like how much are we talking about in round numbers?
So I'd say there's like there's really like three levels. So there is an entry level device called a quark, which is a hydrogen alpha filter that goes essentially at the eyepiece. Okay, not right at the eyepiece, but it's close to the eyepiece. All right. And a quark is, I believe, around $1,000. Okay. The next level up would be a kind of modest size internal Etalon, and these are on the order of $1,000 or $2,000. And the blocking filter is a little bit add on to that. So yes, it is a serious investment. The add-on for the hydrogen alpha imaging is comparable to the cost of the scope. In my case, it's even more than the scope itself. But there's a wide range, and you don't have to have a double Etalon. And in fact, you can see an awful lot with just one Etalon. All you have to do is beef up the contrast when you're processing, and you can see, I would say, most of what you would see with a single Etalon.
Thanks.
So, anywhere from like $1,000 up is kind of the range.
This is Jordan. I can tell you that the quark is $11.99 because I've just bought one about 2 months ago.
Okay.
And if you want to do calcium, you can do the calcium module made by Lunt, which just slides right into your refractor, is also about the same.
So Bob, the second part of my question is more related to observing. I was interested in your comments about how you really have to do some tuning of the elements depending upon whether you're observing detail on the face of the sun as opposed to closer to the limb of the sun. It seems to me I've seen some reportage and some science articles in the past where astronomers can actually look through the sun and detect activity on the far side. Do you know anything about that? Am I imagining that, or is that something that's real?
I think that is real. I actually think that's more like looking in, I actually think it's looking at really low frequency. I think it's looking at ultrasound vibrations.
Oh,
It's,
I
it's,
think
it's,
all electromagnetic fields pretty much, I think because you've got all these ions there, I think they're pretty much impervious.
it's solar seismometry, and it's basically, I think it's based on very high resolution, spectral readings to figure out Doppler shifts in the sun, and then modeling all those details with a complex computer model in order to untangle from the various frequencies. It's like what people do with seismometry on Earth, and so it's sophisticated signal processing basically that they're using.
so thank you guys for all that, and my apologies to Jeannie if I've just sent Bob after some new accessories there.
No,
I would just like to say that this is one of the clearest presentations I've had the pleasure of seeing, and that's including a lot of people who are professional and supposedly doing lectures all the time. So
thank you.
my compliments. I do have a question also. What do you do with your observations other than just your pure enjoyment of creating great images? Are you a member of any organization that tries to do any kind of systematic solar observations?
No, not yet. I mean, I really consider myself to be very much on the steep part of the learning curve on this. I'm getting up there. There is actually a group of people who do solar imaging. There's an organization called Cloudy Nights, basically like a website that's a community of people who do solar imaging. So there's a very strong community there of people who do solar imaging. So we trade and critique each other's images, and that's another very helpful area. Also, for anybody who's interested in any area of astronomy, that it's a free thing. That's mostly what I do. Really, for me, this has been a stress reliever during COVID, and there were a lot of other things that have happened. But for me, just a chance to get outside. And I used to spend more of my time doing nighttime imaging, but I found that was kind of disrupting my sleep schedule. And it's pretty amazing, but almost any morning, like the number of mornings that are clear before, say, 10 o'clock in the morning, and actually the very best time to image the sun is like an hour, just like an hour after sunrise. And you can do everything pretty quickly, right? So I can be up on a Saturday morning and spend a couple hours, taking 50,000 images, and then let the computer chunk away on them for the rest of the time.
Well, I'll just say I believe the Association of Lunar and Planetary Observers, despite the limited name there, has a solar section, and you might want to look into that and see if any of the things they're doing you might want to become a participant in. I think the images you have are just fantastic, and you say you're on the upward learning curve, but I think you're getting pretty close to the top, to be honest.
Oh, thank you.
Bob, I have a question, a couple questions actually. These are equipment related issues. First of all, what stacking program are you using to put all these together?
Okay, so usually what I do, I don't have my flow on here. So usually what I do is I use AutoStacker to do my stacking. But AutoStacker becomes really slow if you try to do like 2,000 images. So what I actually do is use what's called PIP, P-I-P-P. It's another freeware program that you can just run in batch mode. You can just, point it to like 50 files and tell it to go and tell it to pick out the sharpest 10% of all the images and save those, and then let AutoStacker do the stacking on a much smaller number of images. AutoStacker also can run in batch mode. This is one reason that it's really important, is you can run pip in batch mode and you can run AutoStacker in batch mode where it'll process, 100 files if you want, and then you can come back when you're done and look at them.
Are you doing the processing on a laptop or a desktop?
I do both. Usually what I do is I usually take pip and use that to select out about the 10% sharpest frames, and then I store them on a hard disk, and that's like a redundant disk array. And from there, I use any computer to do the AutoStacker. But I commonly do everything on a laptop. It's just slower.
Also, are your etalons, are they Lunt etalons that you have?
Yes. Mhm.
How long have you had those?
I've had one of them for about a year.
Okay.
And the second one, I didn't buy them both at the same time because they are expensive and I wasn't quite sure that I wanted to, invest that much. The second one I bought used. They actually, under some conditions, they'll sell you like a refurbished one. So that's what I did for the second one.
I was looking on the Lunt website and everything is mentioned in terms of their scopes. So I was just wondering, these are generic etalons that they sell by themselves, right?
Yeah, as far as I know, it's only the 100 millimeter that actually you can see. The 100 millimeter etalon you can see as a standalone etalon on their website, but the smaller ones they don't sell.
Okay.
But
Yeah,
there are other places that do.
They used to sell them. That's what got me confused. So you have the large etalons on yours?
Yeah.
Okay. And what camera are you using for this?
It's an ASI 174 mm, which I think is generally recognized to be definitely the best camera to use for this. Mostly, so I mean, a detail when you're fast imaging is you actually want a shutter that like shuts off the entire image at once. I forgot what the technical name for it is, but the shutter mechanism that controls the exposure rate is a little different on this than a lot of other cameras, in such a way that when you give it an exposure time of say a millisecond or two, which is pretty typical for these images, it really is like exactly 1 millisecond. And then the frame rate's fast. I can transfer about 120 frames per second to my laptop through a USB 3 cable.
Hey, Bob.
Thank you.
This was a great talk. I was very interested in all of this. I had a couple questions. One of them was just that, with observing or imaging other things, I guess it would still hold true for the sun that like your aperture size is going to determine what size features you're going to be able to resolve in the ideal situation. I mean, it could be worse than that, but
Yep.
Are these features not so small that like, is this as I mean, it's a decent size refractor, but like a lot of solar scopes are pretty small. And so like, are these features just not that tiny?
Well, the small fibrils, when we get down to looking at these features, I mean,
Yeah.
these are pretty much getting down to the diffraction limit.
Okay.
Okay.
Okay, so I guess it's nothing magical. It's just that they're I mean, they're still pretty tiny, but like that they're not smaller than I thought they were.
No. Nope.
Okay. And then I guess I was also wondering about when you're making the movies, do you like does the software align, like you have the different batches, like 30 different batches. Does the software align each batch for you? And does it use some kind of like feature detection to do that?
Yeah. So for this I usually use IMPPG. Okay, IMPPG is a nice program where it can do sharpening. So one thing I didn't point out is usually if you stack images, you usually want to sharpen them after that.
Mm-hmm.
So IMPPG, you can set up both to do sharpening by two different methods. And you can manipulate the histogram on one image, and then it will apply it to an entire batch. And then
Okay.
you can tell it to align those images, but anyway, you do that, say with 50 images, and then you can tell it to align those 50 images, but don't stack them. Okay.
Okay.
And then in Photoshop, there's a nice feature where you can load the frames into a stack, and you can make that stack then into a animated GIF. There's a nice
Okay.
video on this by a guy named Warren Rigel, R-I-G-E-L, who's has a nice video on how to do this. But IMPPG is
Okay.
a really nice little program.
And then last thing real quick, do you you have your mount set to like a solar tracking rate, but is there also automatic guiding, or is this, I mean, are you aligned well enough with your polar alignment that you just set it to the mount's tracking?
Yeah, well, okay, there's a tricky part of how do you polar align during the day, okay?
Right.
And for that, I'm really proud of this actually. I made a cute little gizmo that's basically essentially a sundial, all right, that has a post, and then it has the altitude and azimuth like on a piece of grid paper. And I simply shoved it up to my mount and get it to within, I mean, I can easily get everything aligned to within less than a degree, okay? I just look up what is the altitude and azimuth of the sun. It's like doing a 1-star alignment at night, okay?
Yeah.
But if it's done okay, then, I mean, certainly for like a minute, you can just, use a compass and point it roughly toward north and you're fine, right?
Yeah.
But like to do an hour-long image, I usually start by using that to get really close. And then there is a special solar guider. Let's see, you can see it right here.
Yeah, I saw that. Is that a piece of electronic equipment, or is it just a physical?
Yeah.
I couldn't really see what it was.
Yeah, no, well, it's got a hole here with the little screen so you can see what it's doing. But no, right up here in the front, it's got a horizontal slit and a vertical slit. And so you can set it and it will measure where is the sun relative to a given point. And it will then do ST4 auto guiding. That's what this white cable here is, ST4 auto guiding from that back. It's not going to be like as good as, a star with PhD2 auto guiding.
Sure. But you don't need it to be, since you're doing lucky imaging.
That's right. That's exactly right.
Okay, well, that's cool.
It actually works pretty well and it's not very expensive.
Yeah. You just needed to keep the sun relatively in the same spot, not to be perfect. So.
Right. Yep. I mean,
Cool.
there are some programs I believe that like fire capture. Some of these programs claim to be able to do feature detection, but what I found is that if you turn the feature detection on, it slows down the frame transfer rate.
Oh.
And what you really want to be able to do is like image just really, really fast.
Yeah.
So,
that makes sense. Okay, cool. Thank you.
Yep. Mm-hmm.
All right, any more questions for Bob?
Just one more comment. You mentioned your daytime solar alignment method using kind of the sundial approach. That sounds like a mini presentation in itself sometimes. So keep that in mind.
Okay, sure. It'll be a short.
Well, if you're patient enough to start your alignment when the sun is rising, and then again when it's high noon, you could drift a line.
There you go. Actually, I do sometimes drift a line. I've done drift alignment, but this thing is a lot faster.
Yeah. Well, thank you so much. This is such a great presentation, and especially for those of us who find it harder and harder to stay up all night. This really is a great and informative and fun hobby. So yeah, great job and great learning over the last year. Thank you so much, Bob.
You're welcome. Thank you.
And before we go, our next meeting is going to be on Friday, October 8th, and I might have just saved the window. We're going to be having as a guest speaker David Lorenz, who's going to be updating us on global light pollution. John, is this the fellow that has done a presentation at our club before?
No, David Lorenz has not presented before, but many of you who I guess, listened to me over the past couple of years know about this website that I love called the Dark Sky Finder, a Google mashup of a lot of data sources to really map out dark sky sources. The guy who wrote that is David Lorenz, and he's a Madison guy. And one of the questions that I have for him next month is why in the heck is he not a member of this group? So we're gonna grill him hard on that. But this should be a good one next month.
Sounds great. Thank you so much, John. I'm looking forward to it. Well, with that, I bid everyone adieu for this month, and we'll see you again real soon.